We have so far discussed the Maclaurin series for the exponential function, for sine x, and for cosine x. Observe that our knowledge of different manipulations on power series, such as differentiation, integration, arithmetic operation, allows us to obtain a number of other related functions in the form of power series expansions. So as an example, let us find the Maclaurin series for f of x equals x times cosine of x cubed, and determine its radius of convergence. Of course, we could go ahead and try to compute derivatives of f at 0, but that would be really cumbersome and really unpleasant. So there is no periodicity for the derivatives of this function as there is for, say, sine or cosine. So this computation will be much more unpleasant. What we should do instead is use our knowledge of the Maclaurin series for cosine. So we know that this is the Maclaurin series for cosine. It converges for all x, therefore the radius of convergence is infinite. Here's how we're going to use it here. Because f of x is x times cosine of x cubed, we can use the expression for cosine x by replacing x with x cubed in it. So we know that the left-hand side is x multiplied with the sum k from 0 to infinity minus 1 to the k times x cubed to the power 2k divided by 2k factorial. What I did here was I replaced x in the power series representation for cosine x with x cubed, because that is the argument of cosine in our function f of x. Let us simplify this further. We have x multiplied by the infinite sum minus 1 to the k, x to the 6k, I have multiplied the two exponents, divided by 2k factorial. And then, since my summation is in k, x is effectively a constant with respect to k. So I can just multiply through this infinite summation by x as a constant and have the following series for my f of x. I just have to increment the exponent on x by 1, like so, and this gives me the Maclaurin series of f of x. Indeed, this clearly is a series centered at 0, and it has the coefficients ck given by this expression. What is the radius of convergence of this series? Again, we have two options. One would be to go ahead and use the ratio test to determine the radius of convergence of this series, just as we would do for any other power series. Or, alternatively, we can say, well, this series is obtained from the series of cosine of x cubed, like so. We know that the series for cosine x converges for all x. So in particular, this series over here will converge regardless of which value of x we put in it. And then multiplying by x does not change the radius of convergence. And so as a result, this series for f of x has infinite radius of convergence as well.